groups are the simplest type of algebraic object that we're going to be looking at. At its most base level, a group is a set with an operation on it. So to understand exactly what that means, first we need to make sure that we're clear on what an operation is. And that's definition 19. An operation, which I'll denote star, on a set A is a function which goes from a pair of elements coming from A and gives something in A back. So we usually write this as in the following way. If A and B come from A, then A star B is the way that we write down the image of the pair A comma B. So the point is that we take an A, we take a B, and we put them together and we get a new element out of the set A. Common examples of operations include addition, multiplication, subtraction, division, composition of functions. Any type of situation where you take two elements in a set, combine them together some way to get another element out of the set is an operation. Now, when the operation star, whatever it is understood, we often write A star B as simply AB. We particularly do this when our operation is multiplication or composition. We notice that under this language, composition is an operation, and we already saw in the last lecture that we sometimes suppress the notation of the composition operator, which is just an open circle. So now that we have an operation, that's actually all we need to define a group. So definition 20 is the definition of a group, and we're going to want to pay close attention to this. So let's let G be a set and star an operation on G. The pair G with star is a group. It's called a group if it satisfies three conditions. So we have a set and we have some sort of operation on it, and we're going to call it a group if it satisfies these three conditions. First of all, we want star is associative, which means that if I take A, B, and C from my set, and I operate B and C together and then A, that gives me the same thing as saying that I operate A and B together first, and then on C, I should get the same thing out of it. So when I have three things all operating together, A, B, C, it shouldn't matter how I group them up. So star should be associative. Number two, there exists an element E in G, and in this course we're always going to use this lowercase e to represent the element that has the property I'm about to describe. There is an element E in G such that for all A in G, A star E equals A, and also E star A equals A. E is called the identity element of the group G comma star. So an identity element is one where if you operate with any element against the identity, you just get back the element that you started with. So think of how if I add 0 to any number, I just get that back. If I multiply any number by 1, I just get that number back. These are the types of things that we want an element to, that is the identity to do. Notice also that I specified that we get A back no matter what order we operate in. The group operation star does not have to be commutative. So it could matter the order that you operate in. So A star B does not have to be the same as B star A, generally. So, and then finally, part 3 is the following. For every element in G, there exists another element B in G such that A star B equals the identity and B star A equals the identity. The element B is called the inverse of A and is, I'll say, usually written as A inverse. Now, using this notation here, I've sort of gotten a little bit ahead of myself. One can definitely ask the question about whether inverses are unique. One can also ask the question about whether identity elements are unique. And it turns out the answer to both of those is yes, they are unique, but that takes a little bit of work to do. However, it is true, and so we're justified in using the notation A inverse to mean the inverse of A, the unique inverse of A, and to use the symbol E to represent the identity because there's only ever one identity in a group. So the first thing that we want to do in order to understand this definition, which is a little bit abstract now, is we want to get a big family of examples that we can keep in mind. Whenever someone says, oh, let G be a group, we want to have some sort of prototypical groups in mind to think, oh, it behaves sort of like this. And in particular, we're also going to have some non-group examples so that we can see how a group with an operation can fail to satisfy these conditions. So let's look at a bunch of examples. Probably the most important example that we should think about is the integers with addition. So the set of integers with normal addition. Let's check and confirm that this is in fact a group. Let's check the group properties. So first, if A, B, and C are all integers, then A plus B plus C equals A plus B plus C, since, well, we already know that addition of integers is associative. Second, we need to know that there's some sort of identity element. So we need to know that there's some element of Z such that when you add it to anything, you don't change that element. That A plus that thing is just A again. The element 0 is an identity for z plus, since for any integer a plus 0 equals a, and we also know that 0 plus a equals a. We know that adding 0 to any element doesn't change it, and so that means that 0 is an identity for z with addition, integers with addition. And then for any element a in z, we need to know that there's something that we can add to a that gets us back to the identity. For any a in z, we have that a plus negative a. So negative a being the negative in the normal sense of the integers, the opposite of a. We have that a plus negative a equals 0, which is of course the same as negative a plus a. Thus, negative a is the inverse of a under addition. Now, the integers with addition are pretty simple. We didn't have to do very much work here to check that it's a group. And in many ways, this is sort of our prototypical group. Every group is related to this one. And it really should be the first example we have in mind of a group. Now, nothing that we did about this example was special to the integers. In fact, if we take the rational numbers with addition, the real numbers with addition, or the complex numbers with addition, these are also all groups, using basically exactly the same argument as we did for the integers. So these are a good place to start with thinking about groups. So let's think about the same set of integers, but with different operations. All right, so let's look at the integers with subtraction. And let's see whether the integers with subtraction is a group. So first thing that we need to check is associativity. And we want to check to see whether a minus b minus c and a minus b minus c are the same thing. Well, if you simplify these things down to where you don't need parentheses anymore, you'll see that the bottom line here just becomes a minus b minus c, reading left to right. And on the top, we have to distribute the negative through, so we get a minus b plus c. So it looks like these two expressions right here are not equal. So it looks like the operation of subtraction isn't associative. Now, this is just what it looks like. In order to actually prove that subtraction isn't associative, we should give a specific example. So we should give a specific example to show that subtraction isn't associative. So we could take the example of a equals 1, b equals 2, c equals 3, for instance. And we can just try this. Generally, if an operation is not associative, you will usually be able to recognize that by just picking three random elements. Usually, if an operation fails to be associative, it fails to be associative almost everywhere. And in fact, any three numbers that you pick, any three integers that you pick, will show that subtraction is not associative unless c is 0. So as long as c is not 0, any three numbers that you pick will prove that subtraction is not associative. So In this case, we can see that a minus b minus c will be 1 minus 2 minus 3, which gives 1 minus negative 1, which is 1 plus 1, which is 2. And then a minus b minus c is equal to 1 minus 2 minus 3, which gives negative 1 minus 3, and negative 1 minus 3 is negative 4. So in particular, these two expressions are not equal when a equals 1, b equals 2, c equals 3, and all you need is a single example for where the associativity formula fails to show that the operation subtraction is not associative, and therefore this set and operation pair is not a group. One thing that this example shows is that it's not enough to just ask, is the set of integers a group? You have to specify a set and an operation, because the same set could be a group under some operations and not a group under other operations. So our answer here is that this is not a group. All right, so let's look at another one. Let's ask, what about the integers with multiplication? So we have that multiplication is associative. And we do have an inverse. One. Because if we take any integer and multiply by 1, we just get that element back. A times 1 is equal to A. 1 times A is equal to A. So 1 is an inverse. So we've got associativity. We've got inverses. Sorry, we have an identity, not inverses. Sorry. We have an identity, which is 1. But the point is we don't have inverses. We don't have inverses because there is no inverse for instance, 2. 2 times b equals 1 has no solution in the integers. So there is no element of z that you could plug in here for b to make this equation true. Because 2 times any integer is going to be even and 1 is odd. So 2 times b can never equal 1. So that means that z with multiplication is not a group. All right. Well, maybe we can try to fix this. Maybe we can say, okay, the integers don't work because the thing that we'd have to plug in here for b would be 1/2, and 1/2 isn't an integer. But it is a rational number. So we can ask, well, okay, what about the rational numbers with multiplication? Well, again, we have associativity. Multiplication is still associative. We still have identity. The element 1 is still an identity, and it's still a rational number. And now 2 has an inverse. 2 has an inverse of 1/2, and it looks like everything in Q has an inverse except for one thing. We don't have an inverse for 0. So 0 does not have an inverse, since 0 times b equals 1 has no solution. The requirements to be a group in terms of having an identity, having inverses and having associativity have to hold all the time. So in order for a set plus an operation to be a group, every single element must have an inverse. When we looked at z with multiplication, most of our elements didn't have inverses. In fact, the only elements that did have inverses were 1 and -1. When we move to the rational numbers with multiplication, almost all of our elements have inverses. Every element of Q has an inverse under multiplication except for 0. And that's enough to make this set and operation pair not a group, because a group has to have an inverse for every single element in it. It's a very strong condition. But we are a little bit closer to having a group. Instead of having a whole bunch of things without inverses, we now only have one thing without an inverse of 0. And so we can in fact fix this now. So let Q star, I want to make that be the set of rational numbers except 0. I just want to take all the non-zero rational numbers. So now Q star comma multiplication, Q star with multiplication is a group, since now every element has an inverse. So we tried working with addition, and we found that lots of our normal sets under addition are groups. And we looked at multiplication, and that was a little bit harder, and we had to work things here. But we did find a group, a set that is a group under multiplication. Notice, though, that once again, whether or not we have a group depends both on the operation and on the set. So for instance, Q star with addition is not a group, since, well, there are several reasons, but in particular, it doesn't have an identity. The identity for addition over some set of the rational numbers would have to be 0, but Q star doesn't include 0. So Q star with addition doesn't have an identity, and therefore it's not a group. Now, the next example is a little bit different. We have to be careful. So let's let G be the set of numbers that are in the interval from -1 to 1. So this is a subset of the real numbers. And let's consider the pair of this set together with addition. So this pair has associativity, because we know that addition is associative. So we have associativity. We actually have an identity. We have the identity 0, because if I take any element of G and add 0 to it, I just get that thing back. And we have inverses, because if A is in G, then minus A is in G. And we have that A plus minus A is equal to 0, which is also minus A plus A. So if we weren't careful, we would say, oh, well, then it looks like G is a group. But here's where we would make a mistake. Addition is not an operation on G. And the reason for that is because we say that G is not closed under addition. So since G is not closed under addition, what that means is that I can take a couple of things in G and do the operation on them, in this case addition, and I'll get something that isn't in G. So when you're going to examine a set and an operation in order to see whether or not it's a group, the very first thing that you need to consider is that function even an operation on G? Because this one isn't. This operation of addition is not an operation on G, because I can take two things that are in G, operate on them together, and get something that's outside G. So that means that G with addition is not a group. And this is where we have to be careful, because if we just looked at associativity, identity, and inverses and forgot about the first part of the definition of group involving an operation, we would be tempted to conclude that this G with addition is a group, and it's not. So we've got to be careful with that. All right, let's see some more examples. The 2x2 matrices with real entries are denoted M2 of R. So M for matrix, 2 to indicate 2 by 2, and R to indicate that we've got real entries. So this is of the form all the matrices of the form A, B, C, D, where A, B, C, and D belong to the real numbers. Now, M2R with addition, matrix addition, is a group. We have associativity of addition as normal, basically because when we add matrices together, we're just adding the individual components together, which means that addition of matrices inherits its associativity from the fact that addition on the real numbers is associative. So addition is associative since addition on R is associative. And we have an identity. The identity matrix for addition is 0, 0, 0, 0, since if we have any matrix A, B, C, D, and we add the matrix 0, 0, 0, 0, we get just the matrix A, B, C, D back. And then we have inverses. The inverse of A, B, C, D is the matrix minus A, minus B, minus C, minus D, which gives us 0, 0, 0, 0. So we have another example of a group here, matrices with addition. Now this isn't really too new. This is basically just using 4 copies of the real numbers, one in each entry of the matrix. We're not even really using the fact that this is a matrix to do anything with it. And so this is what we've got. This group is not, this set M2R is not a group under matrix multiplication, but we'll see that in a second. Now, one thing I want to point out is that all of the examples of groups that we've seen so far have had their operation be commutative. So in all of our examples so far, we've had that A star B is equal to B star A for our examples so far. For our examples of groups so far. We've had some non-groups that didn't have commutative operations. But all of our examples of groups so far have had this, but not all groups do. Not all groups have an operation that is commutative. The ones that do, we give a special name to. So definition 21. So let's let G comma star be a group if A star B equals B star A for all A and B in G, that is, star is commutative, then G is called an abelian group. So the term abelian is named after one of the great algebraists of all time, Abel, A-B-E-L. A group that is not abelian is called non-abelian. So one of the big questions that you often want to ask when you look at a group is this an abelian group or not? Is this an abelian group or a non-abelian group? And so what we've had so far is we've seen that Z plus, Q plus, R plus, C plus, let's see, all the examples that we had last time, or in the last couple of slides, Q star plus and M2R plus are all abelian. All of these groups have the property that the order that you do the operation in doesn't matter for the result, that A plus B equals B plus A, or A times B equals B times A. However, that's not going to be true for all groups. And the best example to keep in mind for that is one to do with matrices again. So the general linear group of 2 by 2 matrices over R is the following. First of all, it's denoted this way, GL2R. GL stands for general linear group. 2 indicates that we're looking at 2 by 2 matrices. The R inside tells us that we're working with entries in the real numbers. And it's the set of all 2 by 2 matrices, A, B, C, D, but that have a condition. They have to have a determinant that's non-zero. So remember that this is the determinant of the matrix A, B, C, D. So if you recall your linear algebra, every matrix corresponds to a linear transformation between two vector spaces. The general linear group of 2 by 2 matrices, it corresponds to linear transformations between R2 and R2, the plane of the plane, that are invertible, that you can undo, that don't lose any information when you translate along them. And the fact that they are invertible is determined by the fact that you have a non-zero determinant here. The pair GL2R comma multiplication, where here this is matrix multiplication, is a group. So let's check that. So first of all, associativity of matrix multiplication. Well, I'm just going to say is well known. What you can do is you can sit down with 3 matrices and give them all a bunch of variables, A1, B1, maybe A1, B1, C1, D1, A2, B2, C2, D2, etc. Multiply them in a couple of different ways and see that you wind up with the same thing. It's a bit of a pain, takes a long time, but it's not difficult at all. So associativity of matrix multiplication is well known. Now we have an identity element, and this is the normal identity matrix 1, 0, 0, 1, the 2 by 2 identity matrix. So first of all, notice that this matrix is in fact in our group because the determinant of this matrix is 1. I'll go 1 times 1 minus 0 times 0. And furthermore, we know that if we multiply any matrix by the identity matrix, we just get our original matrix back. And then finally, we do have inverses. Now, there's an inverse formula for 2 by 2 matrices, and the inverse of AB CD is equal to D over AD minus BC, comma, negative B over AD minus BC over negative C over AD minus BC, and then A times over AD minus BC. And you can check that if you multiply this element on the right with the original matrix ABCD, you do in fact get the identity matrix back. And this formula shows why we needed AD minus BC to be non-zero. If it were equal to 0, then these denominators would be 0, this matrix on the right wouldn't be defined, and we'd have an issue. Now let's see that this group is non-abelian. And just like with associativity, if a group is non-abelian, you will usually be able to determine that just by grabbing any 2 random elements. Try multiplying them one way, multiply them the other way, and see that you get different elements out of it. And a lot of times you can get by with fairly simple elements. Although if you go too simple, you might run into a couple of elements that happen to commute with each other, which is not enough to show that the matrix is, or that the group is abelian. So we can look at the elements 1, 1, 0, 1 and 1, 0, negative 1, 1. Both of these groups have determinant equal to 1, and so they belong to our group. And notice that if we multiply these together, we're going to get a 0, a 1, a negative 1, and a 1. But if we multiply them in the other order, if we take 1, 0, negative 1, 1 times 1, 1, 0, 1, we get 1, 1, negative 1, and 0. So in particular, the 2 results that we get when we change the order of the multiplication are different from one another. And that shows that this group is non-abelian. And it's one of the best examples of non-abelian groups to keep in mind because we have seen matrix multiplication before. It's a reasonably simple group to describe. It's the 2 by 2 matrices with non-zero determinant. But it captures a lot of the non-abelian nature that you can see in arbitrary groups. Let's see another good example. So let's let g be the set of functions from the interval 0, 1 to the interval 0, 1, where f is bijective. So this is actually a huge set. There are many, many, many functions that go from the interval 0, 1 to the interval 0, 1 that are bijective. Note, I haven't required f to be a polynomial or even continuous here. There are a huge number of functions that I could be working with here. All I'm requiring is that f is bijective. And so let's look at the pair g comma composition. Let's check and see whether this is a group. We know that composition is associative. We actually did that in the last lecture. We want to know that we have an identity element here, and in fact we do. We have an identity element, which is just the identity map on the interval from -1 to 1, which sends an element x back to x. If I compose this function with an element f, that's just going to be, and apply to an element x, that's just going to be the identity function of f of x, which is just f of x back, and similarly going the other direction. So that gives us an identity element. And then for any f in G, since f is a bijection, it has an inverse, f inverse, from which we did last time, and we have that f composed with f inverse is the identity on the interval 0, 1, which is also what we get when we take f inverse composed with f. So that means that G with composition is a group. So then the question is it abelian or non-abelian? Well, we may recall that composition is generally not seen as commutative. If I compose f with g and g with f, I get a different result. So to prove that G with composition is non-abelian, we have to give an example. And of course, there are lots of different examples that we could show. So to see whether or not this group is abelian or not, we could take the following functions. We could take f of x, which is x squared. That is a bijection between the interval 0, 1 and itself. And let's let g of x be given by 2 to the x minus 1. This is also a bijection between the interval and itself. But if we compose them in two different ways, f of g of x is equal to f of 2x minus 1, which is 2x minus 1 squared, which gives us 4 to the x minus 2 to the x plus 1 plus 1. And if we go the other way, if we take g of f of x, that's g of x squared, which is 2 to the x squared minus 1. And all you need to do to show that these two functions are different is to plug a different number, is to plug one number into them and see that you get a different result out of it. And so for this one, we could plug 0 in. Oh, sorry, 0 doesn't happen to work on this one. We could plug in almost any number into these things other than 0 and 1 to see that they are different, and show that these two functions are not the same, and therefore our group up here is a non-abelian group. Next lecture, we're going to look at a group defined by equivalence classes under congruence modulo n, going back to our first discussion about equivalence classes and partitions and such, and it's going to be another very fruitful source of examples for us.